I'll be talking about models of energy buildup and explosive release in flares and CMEs. And I also like to thank my longtime collaborators who are working with me on this topic. Rick DeVore, who was a developer of the ARMS code, and I will show you some simulations from the ARMS code. Judy Carpin, we've been working together for many years. Also more recent collaborators, Joel Dalin, James Leake, Emily Mason, Viper, Akash Kumar, and many, many others. So you can see on these two movies, the top movie shows SDO observations, I think 94 or 94, of the series of CMEs of X-class flares that took place in September 2017. And as the sun rotates on the west limb, you can see the famous September 10, 2017 event there with a huge eruption, the CME taking off very fast, object of a lot of attention. And then on the bottom, you see the HMI image, the HMI movie, showing you that all this eruptions and all this activity is due to the actions of the very strong magnetic field in that active region that's coming out. Okay, and away we go. Here we go. I guess I had to press that in order to get the thing to move. So I'm going to be addressing two primary questions. What is the mechanisms for the energy buildup? And then what is the mechanism for the explosive energy release? Another very important question is, where does the energy go? I won't address that here, but that's critical for sulfur. And for this talk, the way I'm going to do it is I'm going to try to kind of describe present understanding. In other words, give a tutorial rather than present our latest and greatest results. The latest and greatest results are going to be presented by Rick DeVore on May 21st. So what I'm going to try to do is bring everybody up to speed on what's the present thinking on the buildup and release. It turns out there's only a few viable theories for each of these issues, the buildup and release. So it's you don't have to learn that much. And I also try to discuss the outstanding issues and opportunities, especially for the sulfur team, and those I'll outline in red. Okay, so the problem with the September 10 events is that the September events is that they're so fast and they come from the small active regions. It's hard to see what's really going on. Good thing about flares and CMEs is they occur at all scales. And so we can look at larger and slower eruptions, and from that, understand how these more energetic, more compact ones work. So here is the sun in all its glory in the 193, around 1.5 million degrees, whatever it is. And what you see here is a filament on the disk, also called a prominence on the limb. You see this dark material, this dark snaky material, and here is where the magnetic field is highly sheared, stretched out along in this direction. You can also see there's another filament going here. It turns on the corner around there, right? And probably this one connects to this one on the backside, but I'm not sure about that. Okay, so when I start this movie, what you'll see is that first, this filament will be ejected outwards. Then this one will be ejected, and you'll see some brightening. That's the flare event, the relaxation after the ejection. And then the third one will finally take off. Okay. So you can see this movie as it plays. There was the first one, second one, and then this third one. Okay. So just by looking at this movie, you can see something about the phenomenon. The phenomenon is physically similar to a volcano. In fact, it's very similar to a volcano. People sometimes describe flares as solar storms, but they're not storms, they're volcanoes. And you know they're volcanoes because they produce shock. A hurricane at the Earth never produces a shock. You only get shocks from something like a supervolcano, like Krakatoa produced a shock that traveled around the world. And just like a volcano, if you think about how a volcano works, what happens there is that you have hot magma coming up from below. It wants to press outwards to escape, but it's held down by a rock cap. And a volcano is due to the catastrophic breakup of the cap. The cap releases very, very quickly. It's not that the pressure from below increases so fast. It's really that the tension from above, the hold down, breaks down and releases the upward push. Now, in this case, of course, if you think about it, you say, well, wait a minute now, this dark material, how's that magma? Because it's cool and it's dense and it should fall down really than falling up. So exactly right. It cannot be that the gas pressure, the plasma, is acting like this, this volcano, this upward push or this downward pull. It must be all due to the magnetic field that's holding this material up and eventually gets tired of holding it up and just throws it out. So how does that work? Here's how it works. Suppose we take kind of like the simplest possible picture for a filament channel for this long stretched out magnetic field. So to form this simplest possible model, let's consider first a dipole field. And here are two views of a dipole field. You can think of this plane as being the photosphere. And if we're looking down, this is your magnetograph. So here's your positive polarity, negative polarity. Here's your polarity inversion line. And these are your field lines for a dipole field. Now, if you consider the Lorentz force for a magnetic field, J cross B, it breaks up into the perpendicular gradient proportional to B squared, right? So it's perpendicular to the magnetic field lines. And then a tension force that's also perpendicular to the magnetic field lines, proportional to B squared again, and it goes as inverse with the rays of curvature. Okay, so there's a tension force just like in a string, and there's a pressure force just like a gas pressure, but it's all perpendicular to the magnetic field. Because J cross B, of course, is always perpendicular. So what happens here, if you think about these field lines, what determines their shape? Well, what happens is that there is, in fact, a B squared pushing upwards, a gradient B squared pushing upwards. But on the other hand, there's a tension pulling downwards, trying to straighten out these field lines. And it's the balance between the up push and the downward tension that determines their shape. Okay, suppose now we just take this system and we just create a filament channel, the stretched out field lines by doing just that, just stretching out the field lines. And we'll stretch them out just the way the sun shows us that they are, very close to the polarity inversion line. These filaments that were on the sun in the previous movie, they're all sit right over polarity inversion lines. Okay, so if we create the filament just by applying a motion very close to the polarity inversion line, a stretching out motion, this is what you get. This is the force-free solution for this motion applied to the photosphere. What you see is that the field lines that are very close to the polarity inversion line and that are influenced by the motion are stretched out, come so. And then the other ones, the overlying ones that are not affected by the motions, they are just forced to respond to the stretching of these field lines. So what happens now is that for these field lines, we've added a component of B in the direction of the polarity inversion line, let's say a Bx. So we've added extra magnetic pressure. This magnetic pressure is pushing upwards these field lines who don't want to go anywhere because they were happy where they were before. That's their lowest energy state, but they're forced upwards by the pressure of these. So these have extra tension to try to keep these guys down. So here exactly is our volcano. Here we have the gas cap right here. I mean, the rock cap right here, holding down the magma right down here. So with this simple little kind of, model, sketch, however you're going to call it, we recreate exactly what we need to get a CME. And actually it goes better than that. If you look at these field lines, this was from a true force-free calculation, you see there's a dip here, right? you get a dip right away when you do this three-dimensional stretching. This is where the cool plasma can sit. And also, if you look from above, you can see this S shape, the sigma shape, the famous sigma shape that you see in pre-eruptive structures. So this simple little kind of stretching thing gives you everything you observe. So it's got to be quasi right in the sense that even if we don't get to this state by these motions, still this must be the state that we see when we look at a filament channel. The other interesting thing about this state, which has always fascinated me, is that if you think about it, it's the only way really that you can store energy in the corona, strong magnetic energy. Now, what do I mean by that? Suppose you say, well, okay, I want to apply these kind of artificial localized motions. Suppose I think of applying a differential rotation so that I have motions that have a large scale compared to this polarity inversion line, okay, like the differential rotation would have. What would happen then, though, if you try to do that, is that the overlying fields, they would just expand outwards like crazy, and they would open up first, and you would never be able to hold down the low-lying fields. You would just get successive opening of field lines. So a large-scale shear flow doesn't work. Also, you say, well, suppose I try, in that case, doing little rotations low down here, little twisting motions. Would that work? Would little twists give me stored energy? And the answer is no again, because in 3D, right, these field lines, these tied down field lines, they can move out of the way. So what you have to do is you have to make it energetically unfavorable for them to move out of the way. And that's what this very long shear does for you. For this blue field line, dark blue, to move out of the way, it would have to extend all the way to the end of the stretch out field lines, which is just too energetically expensive. So really, the sheared field is in some sense the only way that you can get these eruptions. And the sun somehow magically contrives to produce them everywhere. It produces these shear field lines low down along polarity inversion lines everywhere. It's always amazed me, a little bit creepy that the sun would kind of contrive to fire these eruptions at us by this kind of unique process. Okay, so what are the generic properties of the filament channels? One, they're always localized above polarity inversion lines. They involve the lowest lying flux in the corona. They're ubiquitous. They form in strong and in weak field regions, in other words, in active regions and quiet regions and high latitudes, etc. They form in old and new polarity inversion lines. When you have flux emerging, you can see these things appear very, very early on if you have a complex active region, but they also form along old polarity inversion lines. They form along large polarity inversion lines like the ones I showed you that go around the sun in the previous movie, but also in very small polarity inversion lines associated with a coronal jet. So if you have a little parasitic polarity region that appears somewhere in, let's say, in a all positive region, you have a little negative region appear, so you have a little circular, quasi-circular polarity inversion line. Eventually that thing will also wind up getting a filament. So whatever mechanism creates these filaments and these prominences, it is very robust. These structures, the shear magnetic field associated with the filament channels is the free energy source for all eruptions. It's ranging from global CMEs to tiny coronal hole jets. So this is great because that means if we can understand the phenomena on one of these scales, we can understand this for all the scales. The bulk of the free energy is always in the shear. Okay, so that's clearly observed. And as I argued in the previous view graph, you have to have the shear in order to be able to store the energy. So that's the main component for the free energy. a major unknown is how much twist is also in the field, the global twist. The twist is not clearly observed. The shear is definitely clearly observed. The twist is not clearly observed and is widely debated as to how much there really is. If you talk to some of the observers, like, for example, Sarah Martin, she'll say none. She draws her prominence as her filaments as kind of stretched out field lines. But on the other hand, for many of the models, some of the models, you need to have some twist. So the twist, the amount of twist is critical for determining the eruption mechanism. And so this is a big challenge to determine how much twist there is in these filament channels. Another property of the filaments and prominences is that they exhibit a hemispheric helicity preference. And what I mean by that is if you consider the overlying field, let's say it goes from positive to negative, from positive polarity to a negative polarity region, then the axial field, that's the shear component, can be, let's say, either in the right direction or in the left direction. And that direction has a hemispheric preference in that you will find that 80% or 90% of all the filaments in the northern hemisphere have one sense of this helicity, and then in the southern hemisphere they'll have the opposite sense. So that's an important result as well. Okay, what are the models? As I said, there are not that many models for the filament channel formation, and they're associated, of course, with the special properties of the polarity inversion line. So what happens at polarity inversion lines? Well, flux emerges there. And there's a bunch of people who worked on how flux emergence can give you a filament. For the flux emergence, you always obtain, and as I'll show you, always obtain a sheared arcade to begin with, a sheared structure. Do twisted flux ropes form as a result of flux emergence? That is still being debated. It starts with a sheared arcade, but flux rope may form afterwards. That is an area of active investigation. Opposite model is flux cancellation. So flux appears at polarity inversion lines and flux disappears at polarity inversion lines. The way these models work, flux cancellation models, first of all, you always start with a large-scale shear. You have to have the shear to begin with, and then you cancel. These models always obtain twisted flux rope, and I will show you these models. And then finally, there's the helicity condensation models that we've been working on recently. Helicity condensation, shear flows. This model always gives you a sheared arcade. I'll show you all that. Now, these models are for the filament channel only. The structure of the surrounding field is also critical for eruption. So it's not simply the fact that you have the sheared field or you have a twisted flux rope. You have to know something about the overlying field in order to get an eruption. Or there has to be special properties for overlying field in order to get an eruption. Because that really is the cap, as we said, the volcano cap. So only 3 models for the buildup process. There's only really 2 models for the disruption process. So it's good. We don't have to know that much. Unfortunately, still, we have 2. We don't have 1 yet. The 2 models are ideal mechanisms, and I put them all together. There's loss of equilibrium that was originally discussed by Terry Forbes, Adbel Banahoy, and a bunch of others. Kink instability, torsion stability. In fact, some people would argue, like for example, Guillaume Molanier would argue that it's really, you can lump them all under the torus instability, the torus-like instability for all these ideal processes. For the kink, you need a critical level of twist in the filament channel. That implies you have to have a net current in the filament channel, right? To get a net twist, you have to have a current going through the filament channel. This current implies that you'll have a hoop stress, hoop force, trying to make the current wire, shall we say, expand outwards. And depending on the properties of the current wire and the overlying field, you can get so-called torus instability where the thing expands upwards indefinitely. To get this torus instability, you need a special decrease of the overlying field with height. So the overlying field has to decrease rapidly with height. And this comes back to what I was saying before, that the properties of the overlying field are equally important to the properties of the filament channel field. The other class of models is reconnection. And here you have the breakout model, which I will discuss, is one that we've been working on. The idea here is that you can use reconnection to remove the overlying field to break the cap. An alternative model is tether cutting, Ron Moore. So I'm not sure, though, what Ron's latest thinking on this is. Is it that tether cutting prepares the filament channel into twisted flux rope state, so then it can undergo a torsion stability, or is it that the tether cutting by itself can just lead to an explosive eruption? Since I see that Ron is here somewhere, we will ask him later. Okay, for these models, the topology of the channel is irrelevant. In other words, the magnetic field, it could be a twisted flux rope, it could be a sheared arcade, whatever it is, all you need is the external reconnection. For these models, I mean for the breakout. Actually, that's true also for the tether cutting, because tether cutting will convert the whatever you start with a sheared into a twisted flux rope. The breakout mechanism works for a whole range of eruptions, from active region CMEs to pseudostreamers to small jets. So this is a real positive for the reconnection model, especially for breakouts, because for a small jet, if you have a very small polarity inversion line with a tiny filament sitting there, it's hard to see how a torsion stability where you're just going to blow open the overlying field is going to work. But since reconnection is important, then the multiscale coupling is absolutely essential. So here's where sulfur comes in. This multiscale coupling and reconnection is, in some sense, at the heart of our drive center. And for these models, it is front and center. Okay, so let's discuss how these models work. Let's first of all talk about emergence for the filament channel buildup. Emergence is straightforward. Suppose you start from below the surface. You have this is calculations by James Leake. Suppose below the surface you have a twisted flux rope, and you need to have a twisted flux rope below the surface in order to keep the field stay together. Otherwise, the field will just fly apart in the convective region. So you imagine you have a slinky below the surface. This slinky breaks through the surface. So here, this plane here is supposed to be the photosphere, and looking down at the photosphere. And what James Leake has done is that these are, some field lines that were there, background field, going into the corona, going down into the...
Could you comment what is color-coded here from blue to red?
Right, so the blue to red, the color-coded is, you'll see it over here, it's the flux you would see. It's like a magnetograph. It's the flux you would see at the photospheric surface. And it's with respect to the initial flux. So basically, this is strong positive and this is strong negative. And here's the polarity inversion line. Okay, so what happens is that if you imagine the slinky below the surface, the outermost highly twist field, as the slinky emerges, the outermost twist field becomes loops in the corona. And the actual field at the center of the slinky, as this thing emerges, becomes the shear field lying along the polarity inversion line. Straightforward geometric arguments. And once the axis of this twisted flux rope gets to the surface, it's hard for it to rise above there because below the axis you have concave up twisted flux, which is held down by the dense photospheric material. So a twisted flux rope below the surface emerges up to the axis, and the axial field becomes the sheared filament. For these models, you get negligible twist from the emergence itself. This emergence injects free energy and shear helicity into the corona. The only thing about the emergence models, of course, they only apply to where flux is emerging. Here's an interesting calculation that James did. What he did was he said, okay, let me take two flux ropes, one oriented so that as it emerges, its twist field lines up with the background coronal field. When he does that, he finds no eruption. The thing emerges and then it stops. Another calculation is where he takes the flux rope below the surface and makes it so when it rises, it's anti-aligned with the overlying coronal field. What happens there as these fill lines, as the twist flux from the subsurface flux rope comes up, it reconnects with the overlying field, kind of gets it out of the way, and poof, you get an eruption. So this is exactly the breakout mechanism, but coming from emergence. And the thing about this calculation, which is so nice, is that it's kind of self-consistent in that he doesn't do anything to, any special assumptions on how the photosphere behaves or this or that. Just says, let me just take two flux ropes, orient the flux rope, and see what happens as these flux rope emerge into a background field. And you find eruption in one case, and non-eruption in the other case. So this is kind of an honest determination of what is your mechanism, what is your eruption mechanism. And then James has very recently done calculations for, kind of varying the angle from being fully aligned to being anti-aligned. And what he finds is that if the angle of the flux rope with the overlying field is close to anti-alignment, you get these eruptions. If the angle is closely to aligned, the flux rope does not erupt. And if you get in between like 90 degrees, you get basically a mess. Some of the flux takes off, some of the flux does not take off. So this is work that we're preparing for publication now. Okay, so that was the emergence process. Suppose now we take the opposite, the cancellation. How does that work? And here's the cartoon is drawn by Odd van Ballenhooyen and Piet Martens many years ago. The way this works is that, again, you have to have shear first. So you imagine you have some arcade, some potential arcade, and then you take some large-scale shear, for example, due to the differential rotation. Then you imagine that, okay, I have convective motions that bring flux towards the polarity inversion line in order to cancel, because you do see cancellation of polarity inversion line. What's going to happen? Well, if along the polarity inversion line, you get reconnection of this opposite polarity flux coming in, reconnection and submergence of the small loops that are created, and then the long loops are left in the corona. What you will get after a while is a twisted flux rope in the corona. This is exactly like flare reconnection. There's 100% flare reconnection. It's happening along this line. This is in some sense your X line. It's exactly like the flare flux convects in and reconnects along that line, and you get this would be your CME plasmoid taking off, and these would be your flare loops, except in this case the flare loops are submerging. And here's a calculation by Duncan Mackay with Odd of this process where they put in the differential rotation, large scale diffusion, et cetera, and you basically get exactly this picture. Notice, cancellation is not like emergence. Emergence calculations are self-consistent in the sense that the simulation includes the subphotospheric region, part of the convection zone, and lets flux appear from the convection zone as it wants to do. Here, though, you're replacing the convection zone and what happens below with a surface where you're dictating what's going to happen. So this is really a quasi-artificial, right? I mean, you're saying what's going to happen. We have not done, and to my knowledge, nobody has yet done a calculation where you actually have a region with a subsurface convection zone, just like in the emergence, put in some flows and see how flux will actually submerge. So this, I think, is an opportunity for sulfur to perform physical submergence simulation. Let's see if this picture actually works when you put in the full dynamics. Another thing you can do here's to show you in kind of more detail as to how this process works in simulations, how the simulations use this. Here's some calculation that Joel Delin did recently using our code for exactly this cancellation process. So we can use this. He starts again with a shared arcade, and then Joel applies basically convective motions, compressive motions towards the polarity inversion line, and also diffusion. So this red and blue flux, positive and negative, you'll see it'll decrease and also move towards the polarity inversion line, and you'll see the sheared arcade convert into a twisted flux rope. Boom. And then from the side, it looks like that. So I think here's another opportunity for sulfur, because surely there must be a difference in how the magnetic field, the measurements of the magnetic field between this sheared arcade, between this twisted flux rope after the cancellation, and the pure sheared arcade before the cancellation. So I would argue that what we need to do is to perform these kind of calculations, take kind of observed regions if possible, perform calculations for with and without cancellations, get a sheared arcade model, get a twisted flux rope model, and then predict what would DKIST see, because DKIST, in principle, will be observing the magnetic field in the corona. So DKIST may be an opportunity to finally break through and tell us what is the amount of twist in these filament channels. But to do that, we need to kind of prepare, make some forward modeling. Okay, and away we go. So how does cancellation lead to eruption? Here's two interesting simulations by Johan Fannin. They're kind of nice because they show the two possibilities: the kink instability here on the left and the torus instability on the right. If you look at these two cases, the difference between the left and the right is really in the overlying field. See, in the overlying field here, it drops off faster with height. So what Johan did is that in this case, she has a certain structure for the overlying field. It doesn't have this drop off with height that's fast enough to give you torus stability, but you do get, once you emerge enough twisted flux, you do get the kink instability, and the eruption stops around here. Although I believe this one here eventually get more reconnection. Here, because of the rapid drop off of the overlying field, eventually what she winds up with is a pure torus instability, and the thing just takes off. And notice you get reconnection down below. So this is exactly the kind of reconnection that you see in the flare. So the flare reconnection is common to all eruption models. You can't really use the flare reconnection to distinguish what is the eruption mechanism, what is the initiation mechanism, unfortunately. The thing about these calculations is that the fast motion precede this flare reconnection. So it may be possible, this is something that we should think about very carefully, is to kind of measure the precise timing between the fast motions and the heating. In these models, in the ideal models, the thing takes off, the reconnection occurs because of the ideal instability, because of the fast motions. So you would think if we can get precise enough measurements of motions versus heating, we may be able to distinguish, to kind of critically test these models. It's difficult in a real event, of course, because in a real event, you have heating taking place all over, heating occurring randomly all over the place for different reasons, and you'd have to distinguish that from the heating, from the initial onset of the flare heating, and also even with motions, in a real event, you have motions occurring along the filament channels that may, and also up above, that are difficult to distinguish or to kind of separate from the actual eruption, the event itself. Third process is helicity condensation. So how does this work? The basic idea here is that we know that the small scale convective motions, the granules and supergranules inject free energy into the corona, right? That's the free energy that drives you, that gives you coronal heating. And this free energy is liberated by kind of, call it turbulent reconnection. It's not really turbulent, but it's just kind of ubiquitous reconnection, kind of space filling reconnection, small scale reconnection in the corona, nanoflare reconnection that Jim Klimchuk talks about. Okay, so we know the small scale motions are constantly stirring up the magnetic field, creating little currencies and giving you, let's call it turbulent reconnection. We also know that there's a hemispheric rule. The northern hemisphere has more negative helicity, has predominantly negative helicity being ejected into it. Southern hemisphere has positive. So suppose that's also true for the motions that are driving this reconnection. What happens to that helicity, the magnetic helicity? The thing with magnetic helicity is reconnection preserves it. So it doesn't get lost. It doesn't get eaten up like the free energy gets eaten up by the reconnection. So where does it go? Where does the helicity go? Well, we argue that it inverse cascades and piles up at the boundary of a flux system. And the boundary of the flux system is, in fact, the polarity inversion line. So here's a simulation by Kalman and Knizhnik, beautiful calculation, where what Kalman does, he starts with a potential field. You can imagine this is the photospheric plane. Here's a polarity inversion line, this circular blue line. Here's closed flux, black closed flux, and white closed flux here, close to the polarity inversion line. And this yellow flux goes to the top of the box where we apply slip conditions there. So these yellow lines, you can think of them as being open because any driving of these yellow lines will wind up just probably getting out the box. Okay, so what do we do now? Kalman applies a bunch of little motions, two little rotations to kind of emulate what the convective flows will do. Okay, and these flows, you can take them to be fixed in position. You can take them to be randomly located. You can take them to be kind of all in one sign or one or the other, or you can take them to have random amount of helicity, positive and negative rotations, however you want to, as long as there's a net injection of helicity into the system. What you find is that after a while, this helicity, yes, indeed, because of the reconnection and this inverse cascade, winds up piling up along the polarity inversion line. So after a while, these random motions build up a sheared filament channel, exactly as you see in the sun. And the interesting thing about this, it is ubiquitous. It's a ubiquitous process. It doesn't care how big, how old, how small is the polarity inversion line. It'll always build up this this sheared arcade as long as you have a net helicity injected by the motions. And Joel Dehlin has shown that you can get eruptions with this. So here's, if you look at this case, no matter how you drive this, you're not going to get an eruption because first of all, there's a box up here, and you don't have the spherical expansion that you need for it to get a nice eruption. So Joel has done this calculation, this helicity condensation for a system that's appropriate to a dipole active region. Here's a dipolar active region, positive and negative polarity, and a background field. And then he's put on these motions inside this negative polarity region. This is what the region looks like. Look at the side, but it's a true 3D magnetic field. Oops. Again, Joel puts on these motions here. In this case, they're just fixed in position. And over time, you build up the filament channel. And then again, if you look from the side, you will find, guess what? Little dips for supporting prominence material. You'll find your beloved sigmoid, etc.
Aspero, you have about 5 minutes.
Okay, and here you see the classic sheared field wants to expand outwards, and it's held down by the cap. And then Joel finds that if you keep on driving this thing, yep, you will get fast eruption. He gets a fast eruption because there's reconnection up above due to the breakout mechanism. So here's a fully self-consistent calculation in the sense that it's self-consistent means that you put in these little motions. You're not actually driving. You're not forcing the creation of a filament channel. For some reason, my movie is slow, but take my word for it, he winds up with alphanic speed eruptions. And then when Joel looks at the energetics and the timing of this, what he finds is that here's the magnetic energy. It rises because of the buildup of free energy due to the small scale motions and the buildup of the shear along the polarity inversion line. And there's a catastrophic decrease when the eruption takes place. The kinetic energy shows rapid increase. But when he looks carefully at the various timings, he finds that this rapid rise in kinetic energy is preceded by the flare reconnection. So basically what happens is that for these kind of reconnection-driven eruptions, flare reconnection turns on first and helps drive the rapid acceleration of the CME. So what we can do as part of SOFR is perhaps perform similar timing studies for the other models, do the same thing for the other models, see if we can get a difference between the models and what happens first, and then let's look at events and see if we can distinguish what the sun is actually doing. So what is the energy buildup to status? We only have three viable models: emergence, cancellation, and holistic condensation or shear flows. They all work in idealized systems. That's not the issue. The issue is which one the sun is actually using. What I see as opportunities, well, for the emergence, what we really need to do is to calculate emergence on active region scales. The simulations I showed you are for small, kind of like pore type structures. James is now working on active region scales, and let's just see if he does a big region, do we get the same result that you need to have a breakout reconnection to give you interruption, and what would be the structure of the filament channel when you do emergence in an active region scale. For cancellation, what we really need to do is self-consistent cancellation, where we actually have a sub-photospheric region, we put in the flows, and let's just see how flux actually submerges. And do we get a twisted flux for that case? The other thing we need to do is to combine the holistic condensation models with cancellation, and that's what we're working on right now, in the sense that simulations I showed you for holistic condensations, we did not mess around with the polarity inversion line. We did not apply any motions to the polarity inversion line, because once you do that, then you will start to get the normal flux starting to mix in and diffuse together. So we'll do that next to see what happens. The other opportunity I see is, again, combine the models with the new data from DKIS to see if we can make a definitive determination of the filament channel topology. This, I think, is really something that would be exciting to accomplish if we can get there. For the explosive energy release, we have only two models, really torus and breakout. Both, again, have been confirmed by many observations, whatever that means. Opportunities. Okay. I think the kind of simulations that have been done for the flux emergence should be done for cancellation and for the the holistic condensation. Let's try to do simulations, calculations, where we start with a no free energy, build up with free energy, and let's just see how the eruption proceeds and how the energy release proceeds. Get the timings as to what happens first, compare those with observations. I think if we can do that, we'll go a long way towards being able to distinguish between the models. Further issues, though, that are going to be, beyond this is one, particle acceleration by reconnection. I didn't talk at all about where the energy goes. This is a huge issue, especially in terms of, space weather, etc. So the question about how does reconnection accelerate particles, that's a critical one. It's a big one. And that brings in the issue about the kinetics, bringing in all that discussed were global MHD type simulations. We need to now bring in the kinetics and understand how reconnection actually occurs, what are the structures, and what is the effect on the particle distributions. So we got a lot of work left to do, but it's going to be interesting and it'll be a lot of fun. Thank you all.
Thanks, Spiro. Nice talk. Excellent timing. So we are now open for questions, and I remind that we are encouraging early career people to ask questions. Just please do not hesitate. There are no stupid questions, but there are unclarified things maybe. So Sudong, you can unmute and ask your question.
Thank you, Spiro. That's a great talk. So you mentioned that you want to carry out simulation of cancellation with a convection zone. So I was just wondering, what kind of difference do you think it will make compared to the current kind of a surface-driven cancellation without a convection zone?
Okay, so the thing is, if you think about it, first of all, to get this to happen, you are assuming a lot about the photosphere. What you're saying is that the photosphere is a region which is high beta, so it can bring flux together at will, right? It'll reconnect there, but then suddenly, once it reconnects, right above it is zero beta, so the flux can just pop out. So what you're saying is that this flux somehow will disappear, but this flux pops up, right? So you're replacing a finite beta transition with this kind of magical discontinuity in beta. Right? I think it'll make a huge difference once we put in a true region, a true, kind of convection zone, or a true atmosphere, rather than this magical surface. Yeah. For one thing, for example, there was some years ago, there was the argument that, oh, gee, if you have field lines like this, they're touching the photosphere, so-called bald patch regions, then these field lines would be pinned to the photosphere. But that's actually not true. If the photosphere, if you put in a true gradient in beta, then what you'll find is these field lines that are concave up at the photosphere will be able to lift up a certain amount. If they go in deep enough, they won't be able to lift up, but they're going to lift up over a photosphere scale height. So there's a huge difference between the present models, which are assuming a discontinuity there, versus the real sun, where there is no discontinuity. Yeah, I wonder what's going to happen. First of all, it's going to be very tough to submerge some of this flux.
Okay, Brian, your turn. Please unmute.
Thank you, Spiro. Nice talk. One thing that happens frequently in your simulations is that the field, when it erupts, does not open all the way down to the polarity inversion line.
Yep.
By now, you guys have done a lot of simulations in a lot of different geometries. Do you have any rules of thumb or any understanding of how far down it goes, how far down it opens, or what governs how far it opens?
Yeah, so, okay. Maybe I can't show it here because I don't have that particular thing. So it'll depend, right, on how you put in your shear. If you make your shear zone narrow enough, of course, you're going to force the system to open up lower down, right? So the narrower you make your shear zone, the lower down the field will open up. Exactly where the system decides to kind of begin its flare reconnection and to say that, okay, the shear above here is going to get ejected, the shear below here, I can't eject it, it's just too hard. It's just too hard to get that out. I'm not sure if there's any kind of simple way to determine that a priori. You could certainly change it kind of grossly by just like I said, by changing the width of the shear zone. But within that shear zone, where exactly is it going to happen? It's a good question. It's a very good question, Brian. We should work on that. See if there's any way to do it a priori. Because really what it comes down to is what you're asking is how much of the free energy is actually going to be released. Now, the sun itself does the same. You know, if you look, for example, at a big eruption, like, for example, the Bastille Day flare of 2000, you will see that the lowest lying flare groups have a lot of shear in them. So clearly the eruption occurred above the, lowest lying field, so, or occurred in the shear zone, and there was still sheared flux below there that could have erupted but didn't. It was energetic, the unfavorable. And in fact, in some eruptions, I've seen movies where you look down at the sun and you could see the whole dark filament just sits there, and the eruption occurs outside of the dark material. It's in the filament channel, obviously, but it's outside the dark material, so it happened above there again. Yeah, good question.
Okay, next, Ron, unmute, please. And Spirit, keep in mind that there are a long queue of questions. So
Okay, okay.
You're talking to me to talk?
Yeah, sure.
Okay. So I have two things.
Tell me, Ron.
First of all, doesn't Mark Chung do some simulations with the convection zone there and with colliding flux and cancellation?
Not that I know of.
Okay, I thought, Ching Zoglu, who's there with him, has found, collision of flux is important to flare sites. And I thought they did some simulation of one such flare. And I thought they had the convection zone in there too. So you don't know about that?
That I don't know about. That'd be interesting to see. Do they actually build up a filament channel ahead of time, or is it by this?
They get an explosion.
Yeah, well, they get explosions, but I mean, like for example, what Tibor and James Leake are doing simulations where they use the emergence to trigger a
No,
pre-existing
it's
filament.
not emergence. This is collision of two different bipoles.
I know, but the same thing here. He starts with they start with a flux rub already in the corona, and then a different bipole emerges and causes the coronal flux rub to erupt. So the question is, has anybody shown that you can build up a filament channel by cancellation? That's the issue. So, but anyways, send me the reference, Ron.
Okay, it's I don't know. It's Chung the last few years with
Okay, fair enough. Look it up. I'll look it up.
Okay, now the other point is what does cancellation have to do with building the filament channel, right?
Yeah.
I think that was the thing you were asking me about at the beginning. Is that right? More or less?
No.
Tether cutting.
Go ahead.
But so the two kinds of tether cutting. There's evolutionary.
Oh no, tether cutting. You're talking about tether cutting or cancellation?
Both.
Okay, go ahead.
There's a tether cutting, runaway tether cutting in the eruption, but before that, there's slow tether cutting that goes to the cancellation, right? The Van Bohemian type thing, right? It's not fast, it's gradual, it's evolutionary. It's driven by photospheric flows.
Well, okay. So
right. So here's what I think. You get the Van Bohemian gives you this little twisty thing. You say, hey, we don't see twists like this. So there I believe in your helicity condensation, that this is one way to put helicity into the system. And then that gives you your filament channel, the condensation.
Sure, that I can see. That the
guys, I have a question in the chat. Can you explain to people what tether cutting is?
So tether cutting is reconnection that occurs inside the filament channel. Inside the filament channel, you have very strong shear. So in principle, you can get reconnection there. So let me just show you, for example, if I look at here, the tether cutting would be reconnection in here between, let's say, this field line and this field line, let's just say, or the field lines inside here. So that's what tether cutting, and what this tether cutting does is really, you can imagine this process occurs. See this process right here where you have this very strong shear. Suppose this reconnection occurred actually higher up in the corona. This you can think of it as a sheared filament channel, and this would be tether cutting right up here. If this occurred up in the corona. The problem with the tether cutting, Ron, is this kind of tether cutting is that it's not coherent. But anyways, let's go on.
I'm calling this my slow tether cutting right here in this
Call
cartoon.
it- Okay, okay. I would call it random reconnection. And we see that all the time, but it doesn't do much other than perhaps it does.
It
add to-
helps build the channel, perhaps.
It helps build a hill, but it builds a sheared arcade though. It does not build a global twisted flux throw.
No, right. That's what that's what I'm saying. That's what I think.
Yeah, okay. I'll buy that.
Okay, Sunny, next in line, please.
Thanks, Spiro, very nice talk. My question is, are there any observational evidence of helicity condensation? If not, then what kind of observations will provide support our observational evidence for helicity condensation model?
So are there observational evidence? We should be able to see, I mean, you certainly can see the photospheric motions. You can't see the reconnection. We don't see the reconnection that's taking place in the reconnection that's giving you the nanoflare. It's just a statistical effect. Other than the buildup of the filament channel, how would you know it's coming from that?
I'll speculate if I can jump in.
Go ahead, jump in.
We see the radial flux of active regions disperse, but we see the non-potentiality, in H alpha filaments increase with time. So something very different is going on with kind of the transverse component of the field, or the non-potentiality of the field versus the radial field. So we do see a kind of anti-diffusion, and you'll see filaments merge together, and you'll see knots of H alpha filament material link up and build up with time. So we see this buildup, this large scale buildup of helicity, or pardon me, non-potentiality above polarity inversion lines, that behaves very differently from the dispersal of the radial magnetic field, which does diffuse. So there seems to be anti-diffusion in one case and diffusion in the other.
Yeah, I remember Alan Title showing me when Trace first went out. He was so excited. He showed me some movies of exactly that, what you just say, that the little filaments seem to be kind of reconnecting, lining up along the polarity inversion line and forming this coherent structure, which, as you say, you don't see it away from the polarity inversion line.
Okay, Chill Jump.
Hi, nice talk, Spiro. So my question is kind of in line of the previous one. So how do we use observation to distinguish the cancellation model and the helicity condensation? Because both of them seems to building up a shear in the filaments.
Okay, so what the cancellation model builds up a twisted flux, or builds up the twist. So the way to use it is to, the way to distinguish between the two is to ask the question, actually, independent of the model, it is critical that we measure how much twist there is in filament channels. Never mind which model is correct, but the measurement of twist in the filament channel is critical. So what I'm proposing is that we do some forward modeling. It's going to be tough. Perhaps it's possible that when DKIST starts observing magnetic fields on the limb, it'll show us right away, say, oh, look, here's a circle, or there's no circle. That would be great. I kind of doubt it. I think we're going to have to do forward modeling and say, okay, let's run the cancellation model as is right now, just with all the assumptions in the photosphere. What kind of filament channel would it predict? Especially, if you need a filament channel for that, that's has enough twist for a torsion stability. Let's run the helicity condensation model. What kind of shear does it predict? Let's compare with the DKIST observations. We need something new because we've been looking at these things for decades and haven't made a definitive determination of the amount of twist. But hopefully, maybe DKIST can make this, will provide the new observations. And maybe GST. I don't know if GST has the wherewithal yet for measuring magnetic fields on the limb.
Okay, Hugh Hudson, please. Hugh, you are muted.
Right. Thank
Yeah,
you.
go
Thank
ahead.
you. And thank you, Spiro, for a very clear talk, which you frequently discussed helicity, which is really hard to observe, but you never mentioned the chromosphere. So my question is there any value added by physics in the chromosphere in the context of these global considerations for stability and eruption?
Well, so for the cancellation model, that's the whole point, that the chromosphere is the transition from the low beta to the high beta. So I would argue that if you want to do the cancellation correctly, you would have to include the chromosphere. Now, the emergence models are doing a better and better job now, more and more sophisticated treatment of the chromosphere. The thing with the emergence models is in a sense, it's kind of easy because the magnetic field is naturally buoyant, so they just put the field in there and poof, out it pops out. It's a tough calculation. I don't want to minimize it's very, very impressive work that the emergence people are doing. We got to do the same thing, including the chromosphere in the cancellation model, to see what do we get when we put in a physical cancellation.
So what difference would it make? I mean, would it be the time scale of the process, or how does the chromosphere help you to determine the global structure?
So here's the question. The question is, would you actually get towards the flux of once you put in the chromosphere? Because you can see that the chromosphere would either trap magnetic field as it tries to emerge or prevent it from submerging, right? So I think it can make a huge difference to what you see in the corona. And we don't need to put in a chromosphere that's kind of has all the bells and whistles. I'm not saying that we need to understand chromospheric heating and all that kind of chromospheric structure, but we need to put in kind of the gross dynamics of the chromosphere when we're considering the photosphere to corona transmission. If we're doing something like cancellation, I mean, if we're doing something like, well, we're just moving foot points around and looking at coronal heating, sure, we don't need perhaps the chromosphere. But if something like cancellation, we definitely have to put it in there.
Okay, so I think we do not have any raised hands and unmuted microphones, and the time is basically over. So let me thank speaker and the participants for this event, and please rejoin us for April event about Type-3 bursts. So thank you very much. Have a nice month.
Thank you, everybody. Thank you.